Hi, everyone. I wanted to go ahead and get started with a kind of preview, or maybe not necessarily a preview, but I wanted to talk for a moment about the topics that we've been discussing recently. We've been discussing protein structure, or we've been getting toward protein structure, and we've been doing that by looking at amino acid structure. So at this point in time, one of the very important things that we've discussed is we have discussed the structure of our 20 proteinogenic amino acids. And with that in mind, we've talked about the single letter codes and 3-letter codes of them, as well as the full names. Now, one of the things that we've talked about with respect to them is how those different amino acids, or what an amino acid looks like, and then how an amino acid changes based on the environment that it's in. Now, for the purposes of this, I want to go ahead and draw a couple of different things. One, I want to draw the amino acid that is signified by the 1-letter code D, which is the 3-letter code ASP, and the full name, aspartic acid. Okay, then I also want to go ahead and draw the amino acid signified by the single letter code S, the 3-letter code SER, and the full name, serine. Okay, now if we compare and contrast these two amino acids, there's a couple of things that are worth noting about them. Both of these amino acids would be classified as polar. Actually, you know what? I'll revisit that in just a moment. The first thing that I'm going to do is I'm going to draw these amino acids at a pH of 1. Aspartic acid, CH2, and then I have a carboxylic acid here, and that carboxylic acid is protonated. Okay, I need to add my positive charge there. Serine is going to look like this. And have an OH group. Okay, now if I look at these two amino acids at a pH of 1, both of these amino acids have an overall positive 1 charge. Now, with that in mind, I want to go ahead and classify them. And keeping in mind, when we talk about classification of an amino acid, we're only focused on this so-called R group down here. Now, for each of these amino acids, what I want you to recognize is that there are two functional groups. There's an alcohol, which is right here, and then we have a carboxylic acid right here. So these two amino acids are classified as polar due to these R groups having a pole to them. There's electronegative atoms that are going to be pulling that electron density in one direction. So these two amino acids are both classified as polar. Now, when you look at these two amino acids, one of them, if you were to imagine it at neutral pH, well then things are going to change about those structures. Now, aspartic acid is classified as a polar negative amino acid, whereas serine is classified as a polar uncharged amino acid. Now, with that in mind, what I'm going to do is, keeping this structure right here, I'm going to go ahead and draw these two amino acids at a pH of, let's go ahead and call it 7. Now, before I do that, I want to go ahead and give you the pKa values for each of these groups, which I previously mentioned. pKa values are not something that you're expected to remember, and I will provide you with them. So the N-termini for aspartic acid has a pKa of approximately 9.82. Aspartic acid C-termini is 2.09, and the R group has a pKa of about 3.86. Okay, now imagine that I'm going to redraw that pH of 7, what I want to do is I'm going to put a star by each of these groups that will be different because of the pH. I'm looking at my two pKa values, 3.86 and 2.09. Both of those values are below 7. And as a result, those groups are both going to be deprotonated. Meanwhile, this 9.82, my pH of 7, is below that. Or my pKa, 9.82, is above the neutral pH of 7. So that group is going to be unchanged. So I'm looking at a molecule. I'm going to draw a line to separate. H3N plus. I'm drawing my alpha carbon. Now I'm drawing my C termini. That's deprotonated. CH2, C double bonded O, and now the single bonded O with a negative charge on it. Okay, so here's where that definition for a negative comes from. My R group is negatively charged at a neutral pH. Now, at a pH of 7, this molecule has an overall charge of, that would be, here's a negative, here's another negative, but here's a positive. So overall, that's going to be -1 because one negative is canceled out by one of the positives. Okay, my other amino acid here, serine. Well, if I were to draw that at a pH of 7, redraw at pH of 7. Now, serine is an interesting amino acid because if you look at the R group, and this is a little bit funky. Some textbooks, you'll see an R group pKa value listed. I'm not going to give y'all one because that OH group is generally going to remain protonated. But the N termini has a pKa of 9.15. The C termini has a pKa of 2.21. You might look at those numbers and say, well, why are they different? Well, they're different. The N termini for serine is different from the N termini of aspartic acid because, well, the makeup of the molecules are different. So those pKa values are going to be a little bit variable. However, they remain within kind of the same general range. Okay, now if I redraw this molecule at a pH of 7, I'm looking at something like this. And actually, before I proceed, I'm going to put a star by the groups that are going to be changed based on my pH being 7. I only have my C termini that can be deprotonated, therefore that's the only group that is going to be deprotonated. Plus, go to my alpha carbon, then my carboxy, that's going to be a carboxylate ion, CH2, OH. Okay, so at a pH of 7, this molecule has an overall charge of 0. Okay, now does that mean that's the molecule's PI? No, it does not. But this just means that the predominant, the most commonly found form of serine is going to have a charge of 0. Are there also going to be copies of that molecule with a +1 charge? Yeah. And are there going to be some with a charge of -1? Yeah, but those by comparison are going to be in very, very, very low concentration. Okay, so this is my overall structure for 2 of my amino acids, aspartic acid and serine. This is an example of a polar negatively charged residue. This is also an example of a polar uncharged amino acid. Now, as we look at amino acids individually, it's also important to think about an amino acid as a building block because an amino acid it's a standalone molecule, but it's also a building block of a larger molecule like a protein. Now, to draw a very simple, what's known as a dipeptide, and actually, I'm going to go ahead and let's see if I can do this. I'm going to pause real quick. I'm going to draw what's known as a dipeptide. Now, this dipeptide is going to consist of these 2 amino acids that I just drew. And they are going to be, the dipeptide that I'm going to draw is ES. So on the N termini, I'm going to have an aspartic acid. And on the C termini, I'm going to have a serine. Now, if I wrote DS versus SD, these are different. What makes them different is the first amino acid listed is that which is on the N-termini. And in this one right here, I've listed D, or aspartic acid, as my N-terminal amino acid and S as my C-terminal amino acid. Whereas this right here, this dipeptide, SD, that has serine on the N-termini and aspartic acid on the C-termini. Now, like I said, though, I'm going to draw DS. Now, a great question that comes from this discussion is, well, how do we form a peptide bond? Well, if we go back here and we look and imagine that we are in an environment that has a pH of approximately 7, we get a good sense for what our molecules are going to look like. And what I want you to recognize right here is we have a carboxylate ion and this positively charged amino group. Okay. Now, what we are going to basically walk away with when these two groups react with one another is something that looks like the following. So I'm just going to take this and this and put them together. So I'm going to have a C. This is going to my alpha carbon right here, but I'm just going to be focusing on the atoms that I drew. Double bonded oxygen, N, single bonded hydrogen, lone pairs of electrons, and going to my next alpha carbon. So the 1, 2, 3 atoms here and the 4 atoms here are going to combine and leave me behind with only those 4 atoms. So if we go from 7 atoms down to 3 atoms, where did the remainder of those atoms go? And actually, let's go ahead and take stock of what's gone. This oxygen right here is that oxygen right here. This carbon right here is this carbon right here. This nitrogen is that nitrogen. One of these 3 hydrogens goes right there. So effectively, what's happening is I'm losing 2 hydrogens and 1 oxygen. So if you have 2 hydrogens and 1 oxygen, we're releasing H2O. And this is known as a condensation reaction, where we are producing water through this reaction. So a peptide is, or a peptide bond, which is what these 4 atoms are, a peptide bond is going to form through what's known as a condensation reaction. Now, what I want to do is take a moment to draw a dipeptide. And we'll do that right here. So our dipeptide at a pH of 7. And I'm going to bounce back and forth to kind of revisit what the amino acid R groups look like. But I've got a dipeptide that my backbone is going to start with this right here, the N-termini for my aspartic acid. So I've got H3N, go to my alpha carbon, then I go to the carbon that is within my peptide bond. It's going to have a double bonded oxygen to it, then to the nitrogen within my peptide bond, which has a lone pair of electrons and a hydrogen. Then I go on to my next alpha carbon. Then I go on to where I conclude, which is this right here, the C termini of my serine, which looks a little bit like this. Okay. Now, keeping in mind, this is at a pH of 7. I know that my pKa for my backbone, I've got a 2.21 for the C termini of serine and a 9.82 for the N termini of aspartic acid. Now, a great question to think about here is, what do I do with these 2 pKa values? Are those relevant? Do those matter? And think about it as when we were drawing these individual amino acids, those groups were free. They were reacting with the environment. But now we're talking about them being a part of a complete unit, a dipeptide, where, well, are we really working with a carboxylic acid and amine anymore? We're not. Instead, we have this bonded, or this peptide bond that results. So when you think back, and I'm sorry to jump back again, but these 2 pKa values, we no longer care about them because those groups have reacted with one another to form a peptide bond. So this effectively is what our backbone looks like. I just have to add 2 more hydrogen atoms on my alpha carbons. That's your simplest form of your backbone. At a pH of 7, without my R groups accounted for, this overall molecule has a 0 charge. Now, with that in mind, we have to go back and add the R groups for the aspartic acid and the serine. Now, for the aspartic acid, I'm looking for my cursor, which I've lost at the moment. Uh-oh. Yeah. Everything frozen. It looks like it has. Sorry, I encountered some technical issues there, so I had to redraw this. But here's my dipeptide. I'm going to go ahead and highlight or put a box around my peptide bond and the atoms within my peptide bond, because I'm going to discuss that in just a moment. But to draw this dipeptide at a pH of 7, I've got my aspartic acid that is deprotonated. I have my serine R group, which is CH2OH, which is protonated. The overall charge of this at a pH of 7 is, well, here's a negative, here's a negative, here's a positive. Okay, so the overall charge of this is -1 because one positive is canceled out by a negative, leaving behind a negative overall. Now, calculating the charge of a molecule like this is just as simple as calculating pi. Now, if you remember whenever we were talking about calculating a pi of an amino acid, what we had to do is we had to think about all of the ionizable groups. Now, I'm going to put a star by all of the ionizable groups on this dipeptide. Now, notice I did the N-termini of the aspartic acid, the R group for aspartic acid, the C-termini for the serine. I, again, did not have to worry about the C-termini of aspartic acid, and I also didn't have to worry about the N-termini of serine. The reason is because they're within that peptide bond. Now, an important thing to recognize about a peptide bond is it's not going to have an overall charge, because let's look at this. This is actually a resonance stabilized molecule, or resonance stabilized portion of our molecule. So this double bonded oxygen, well, it's shorter than a single bond, but longer than a double bond, because what happens is this resonance stabilization ultimately leads to a distribution of that charge. So that puts basically these 4 atoms in the exact same plane as one another. Now, that's a little bit more information at this point in time than you need. But the important part about this is that the peptide bond is never going to adopt a charge. So we only have to worry about these 3 groups. But it is important to remember which groups you're concerned with. So are we concerned with the N-termini of serine? We are not. For this peptide, we are only concerned with the N-termini for aspartic acid, which that group, the N-termini of aspartic acid, has a pKa of 9.82. Okay. We are also concerned with the R group for aspartic acid, which has a pKa of 3.86. And then finally, we are concerned with the C-termini of the serine, which is 2.21. Okay. Now, if you remember, the way that I always like to approach this is I always like to visualize this molecule when it's fully protonated. And this is pretty easy to do because I'm just going to do that, put a hydrogen there, put a hydrogen there. Okay. Now that I have my molecule in its fully protonated form, I'm going to account for my charges. The only group that has a charge on it is my N-termini. So that means at the lowest possible pH, this molecule has a possible charge of +1. This molecule is never going to be +2. This molecule is never going to be +3. +1 is the farthest that it can go. Now, with that said, I'm going to draw an arrow to, well, what's my next group, or what's my first group that's going to be deprotonated? The first group that's going to be deprotonated is the carboxylate ion, because that's my lowest pKa value. And whenever that group is deprotonated, I form the molecule in its state where it has an overall charge of 0. So the next group that's going to be deprotonated is my next lowest, or my next highest pKa value of 3.86. And whenever I have looking like that, that molecule is going to have a charge of -1. The last and final group that can be deprotonated is my N-termini. That N-termini, when it's deprotonated, well, it's going to have hydrogen, hydrogen, and a lone pair of electrons on it. No charge whatsoever. So what that's going to mean is my two carboxylate ions will each have a negative charge. So this molecule can have a -2 charge. Now, with that in mind, this molecule can never have a -3. This molecule can never be -4. But the question at hand is, how do we solve for the pi? Well, I've listed out my possible charges. Now all that I need to do is take my pKa values that I know, or that I will be providing y'all with, 2.21, and list them in increasing order. 2.21, 3.86, and then 9.82. I always make a point to write those numbers above those arrows, so I see that is the pKa where I see a transition from +1 form of the molecule to 0, 0 to -1, -1 to -2, and so on. So my pi is going to be, what are the pKa values that flank my 0 overall charge? So I'm going to say 2.21 plus 3.86, close parentheses, divided by 2, gives me approximately, let's see, that would be 6.07 divided by 2. It's going to be about 3.035. 3.04 for the sake of rounding and significant figures. So my pi for this molecule is approximately 3.04. Did I have to use all of my pKa values? I didn't. I only had to use 2 of them. I only had to use the ones that flanked that 0 overall charge. All right. So whenever you're looking at drawing a peptide and calculating the pi for that peptide, go back to these fundamentals. List out the charges, and then list out the corresponding pKa values. Keeping in mind, aspartic acid had an N-terminal pKa value that was different from the N-terminal pKa value of serine. So you don't want to make the mistake of using the wrong pKa values. I will always provide you with those pKa values so that you can use those as a reference whenever you're encountering this sort of problem. All right, well, I hope this is helpful. Have a good one.